Okay, so I am very happy to be here today with you to talk about something pretty fun, which is 3D printing stuff with Clojure. So when I say stuff, I'm talking about the things we use every day, like for example headphones. We all use all sorts of stuff every day, and they do have a problem. They do break. And in itself, it's not really a problem, but the problem is that because of this, when they break, they are most likely to end up in a place like this. And if you step back for a second and think of it, it's kind of doesn't make any sense. It's like something we really don't want to happen. Things that we use every day just break, we cannot repair them, they pollute for being created, and after being created, when they end up in a landfill, and they also private you from something that is very nice, which is the simple joy of building stuff. So we really want to step back and think about how we can change that thing. People are just happy to build stuff, and I think as programmers, we are all very happy to build stuff every day. So the way to change that mode of production is already known, is open source hardware. Today I'm going to try to make the case that we can use Clojure to build open source hardware. Maybe we can turn ourselves, all of us Clojure programmers, into artisans of open source hardware. So why Clojure? By using Clojure, we will buy ourselves a few things. The first thing is that when you use Clojure, you have the ability to run your program anywhere and anyhow. This is not the case with traditional 3D modeling environments like Rhino or Katia or whatever, which are just clicks in a user interface. But when you use Clojure, you will be able to run your code anywhere, anyhow, and do all sorts of crazy things like, for example, CI for your 3D models. The other thing you get from using Clojure is collaboration. Because you're using code, you can collaborate and code with other people. You can do pull requests on repositories, etc. Things that you would not be able to do if you were using a desktop application, because that would just be clicks in a user interface. You also get composability, which means that we are able to build libraries. For example, if we use some kind of screws or bolts or whatnot, we can build a library to share that library with everyone that wants to use that kind of screws, which is still not the case with desktop applications. And the last thing we get is functional modeling. By using functional programming, we are able to model our shapes as data transformation, which is much nicer than other way of modeling that will use imperative programming, for example. And we also get something pretty cool, which comes from interactive programming. I will try to convey that feeling to you through the demo, but one thing you get by using Clojure for building stuff is that it just feels like the magic. I will try to show you that. So, functional 3D modeling. Sorry about that. You can't really talk about 3D without having 3D titles in this slide. So how do we model shapes with functional programming? There are quite a few ways to describe shapes to your computer. The most simple of which is polymesh, which is basic points in space. Polymesh is nice because it's simple, but you can't really build anything with it. It's too low level. There are other techniques like Bezier curves and nub surface, which are also pretty cool, but a bit complex for us. Let's say that it's going to take much more complexity to achieve things. One simple way of building stuff is constructive solid geometry, which I call CSG, which is basically a way to build shapes by using 3 essential operations, which are just union, difference, and intersection. If you know these three operators, you can basically build anything. And it also has some nice properties because with CHD you cannot build a model that would not be able to be 3D printed. Basically you can build impossible shapes. Also CHD has the advantage of being able to be represented as Clojure code. So if you want to, for example, build a thing here, you can make a few operations that could easily translate to this code on the left. So we are not going to be using Clojure and Clojure only. We are going to be using Clojure with OpenSCAD. OpenSCAD is a CAD modeling free software. It's basically a free software that implements CSG. It is really nice, but it has a small problem of using OpenSCAD script, which is basically a language they created for OpenSCAD, but it has a lot of problems. It's really hard to read, hard to write. It's a language that you don't really want to use. So we're using Clojure with OpenSCAD, and this is all things are going to work. We are going to have high-level Clojure code describing our CSG operations with unions and difference and intersections. And this Clojure code is going to be translated to OpenSCAD scripts, which will then be able to translate to STL, which is the format described in Polymesh. And once you have an STL, it's really easy to print it, to get it printed. So let's get started with a live demo. We will, if you remember, I opened this talk by talking about headphones. We will try to build something like this, some kind of base where we will be able to fit a speaker. So yeah, that's going to be something we're going to build. I just started a project. It almost has nothing in it. It just had this dependency, UNSCAD CLJ, which is basically a library that will translate Clojure code to OpenSCAD script, as I showed in the diagram before. So if you want to build our speaker base, we will just try to get first a number of random tuning. Let's say we will have a simple cube, which will describe as shapes. First, let's import the OpenSCAD library. So OpenSCAD library basically exposes you all the methods you have in OpenSCAD. So if you want to have a cube, you just call this function, which is a function that creates a cube in OpenSCAD, obviously. So this is going to create a map that is going to be ingested by another function, which is scale, right? Scale shapes, which is going to translate our map to OpenSCAD script. So we are going to write that to a file. Okay, and once we have this file, we can open it in OpenSCAD. And the nice thing we have with, you can see it is pretty cute. So you can see it's pretty cute, and the nice thing with OpenSCAD is that it automatically reloads the file as you open it. So the setup with Clojure is kind of seamless. So this is a cube. If we want to demo some basic properties of CSJ, we can start to, for example, make a hole in that cube by using a reference. So let's start with our cube and have another cube making a hole through it. So this is it. With simple operation, we will be able to build everything. So let's start to build our speaker base. We will first try to have something that looks like a tube where we will be able to fit our speaker. So for that, we can use a cylinder. So this is a simple cylinder. If you want to make a tube, we just have to make a hole through it, like we did for the cube, by using a difference. Okay, so here we have something where we will be able to fit our speaker in. Let's also have some kind of let's also have some kind of base where the sound will be able to go through, but we will be able to hold the speaker. So this is going to be called the tube, and we are going to have shapes that can do this, plus the base. Okay, so here we have this. You can see that OpenSCAD automatically puts your object at the center of the screen. You can change that easily by just telling him not to do that. Okay. And if we want to have a speaker in this, we're going to need some holes so that the sound can just get out of it. And for that, we can also continue to make holes with difference. So let's say we are going to have a small hole. Okay. One of the things you can see is that by default, OpenSCAD doesn't use that much computing power, but you can change that easily by how much faces do you want for your models. So let's say we want 64 faces. Things start to get much nicer. But I'm not a sound engineer, but this is not a proper way of getting sound out of a plastic base. So let's make some more holes. And this is where things start to get interesting. So this is where things start to get interesting, because we will be able to use pure Clojure code to build a feature that do not exist in OpenSCAD. So let's say we want to have, for example, 6 holes. We can build a function that will copy the hole around the circle so that it looks like a speaker. So we can build that function with Clojure code. Let's call it circleify. Its main goal is going to copy object around the circle. So it's going to take a radius, which is going to be how much radius you're going to move your object from center. We are also going to have the number of objects we want to copy, and finally take the object. So what we can do is first calculate the angle with basic trigonometry. I'm not going to show you the trigonometry circle, but I'm pretty sure you remember it from high school. So we are just going to divide 2 pi by the count of object. And then we will be able to use that angle to repeat the object with a rotation. So an easy way to do this is to start with a sequence, with a range, and then map the sequence to transform it into an object that will be translated and rotated to the right. So let's pass this range through our function, and we will be able to. Let's first do something. Let's pass this object through OpenSCAD transformation. So let's first move it from the center, with taking the radius. So let's move it from x to the amount of the radius. Let's also rotate the object we're going to copy, which is still pretty easy with OpenSCAD. We are going to rotate it by the angle, but not only by the angle, but by the angle multiplied by the count. Okay, so I believe that's it. Let's pass our object to the function of ReClojure. Let's say we want to move it from 10 millimeters and have 6 of them. Okay. Okay, I forgot to multiply it by. And then you have your objects that are easily copied. There is also something that's lacking in OpenSCAD, which is an easy way to have a cross-section, but hopefully we're using Clojure, so we can just code this feature. So let's define this function. Let's call it slice through. If you want to get a cross-section, we can just make a difference between what we built and a pretty big cube. So let's just do that. Difference between the object and a really big cube that will move to the side. Okay, so let's pass our object to the slice through function. Let's say I'm not sure what's wrong with it. Should be working this way. Let's put that on the demo effect. That you get what I mean. I promise this will work. I think I had it somewhere. I achieved by having it there. Okay, so finally we can get something like this. So this is the modeling part. And then we can get to the printing part. So you have several ways of printing your model. So just if you print it, you will be able to get something like this, which I can pass through the audience. And you have several ways of printing what we just modeled. But the most simple of which is FDM. Many of you probably know what it is. It's just a hot wire that is extruded and melted to form a shape. It has problems. Its main problem is that it needs supports, so you cannot build really complex shapes. You also have SLA, which is kind of like FDM but using resin that is solidified through a laser. One of its advantages is that it can provide prints of great quality, but it also needs support like FDM. And the last way the last common way of printing stuff is SLS, which is basically a laser that goes through powder and solidify powder with its power. It's really great because the quality is really great, and you can also have some really complex shapes inclusion because the powder acts like a support and you don't need support like you need with FDM. So I don't print myself shapes, I use this kind of service to print my models. I'm not affiliated with them, but I'm very happy with what they provide. It's a simple way to get your model printed without having a printer. I don't know if you can build anything, but I'm trying to build headphones. So I'm going through the process of iterating through models, printing them. You can see here what I'm trying to do. And I'm currently trying some different models. I will be putting some parts maybe in the hacking room so you can play with them. And so yeah, that's it. I just wanted to thank people from my last slide, people from the Paris community, people making conference happen last minute for like this conference. So thank you everyone, and thank you.